Greetings and welcome, friends. Mr. Waddy here. We're starting a new chapter, and we are talking about similarity. Now, we have spent probably, I don't know, you guys were here like 4 or 5 chapters talking about congruence of figures, and when two figures are congruent, they had congruent angles as well as congruent sides. We did spend that little bit talking about transformations, and you might recall that in the case of dilation, that a figure changed in scale, that its angles maintained congruence, while its sides were proportional to each other, right? Actually, in this drawing here, we would consider K to be our scale factor. And it turns out that you can describe and talk about the corresponding parts of similar polygons. I realize here we're just talking about triangles again. You might remember CPCTC, right? Corresponding parts of congruent triangles are congruent. And it turns out that corresponding parts of similar polygons have some function and features as well, where all of the angles are still the same, all right? All of those angles, right? Angle A is going to be congruent to angle D, but the side lengths have been scaled up and are proportional to each other, all right? And if I only had 2 side lengths and didn't know the scale factor, if I didn't have a way of translating those two things, I actually wouldn't be able to then tell you the new side length. But if I had 2 side lengths on each of these, actually I'd need those 2, I could set up a proportion comparing those things and then solve that proportion, which actually we had just practiced a moment ago by cross-multiplying. Perhaps you remember. So let's take a look at example 1 together here. I'll grab my snapshot like so. And here we are. So example 1. So in the diagram, triangle RST, oh dear, is, what's that crazy symbol it's showing us? A little squiggly. It means similar, right? Remember, this means equal, this means congruent, and just the squiggle, just the tilde, means similar. So it says find the scale factor from triangle RST to triangle XYZ. So I'm anticipating that scale factor is actually going to be decreasing it. So the value of K is going to be somewhere between 0 and 1. If I want to find that scale factor, what I'm going to do is compare the similar sides. So we could compare, let's say, the 12 and the 20. So the scale factor K is going to equal the new value, what we used to call the image back when we did dilations or transformations, over the pre-image, right? So 12 over 20. And then I can reduce this. What goes into both 12 and 20? Yeah, 4. So 4 goes into 12 thrice and into 20 fifths times. So the scale factor is 3/5. And notice that's true for these 2 sides, RS and XY. It's also true for all of the other sides if these are truly similar, which they told us they were, so we're going to believe them. We're going to believe them. So there's my scale factor. For part B, it says list all pairs of congruent angles. So let's see. So angle R is congruent to who now? X, yep. Angle S is going to be congruent the angle Y, and we are using the congruent symbol because these angles are still the same size. All right, these did not change, only the proportions of the sides were changed. And then angle T is going to be congruent to angle Z, right? So that's nothing too interesting. And then it says write the ratios. So a ratio is going to be a fraction with no units of the corresponding side lengths in a statement of proportionality. Oh dear, wow, fanciness. So let's see, so that is going to be something like this. So RS over XY, and the way I set this up, I also could have done XY over RS, wouldn't have mattered. So RS is to XY as, let's say, RT, so I'm going from big to little, is to what side? XZ. And that is as TS is to ZY. All right, and I ended up doing big over little here, but they also could have been done the other way as well. So all of those are going to be proportional to one another. The key is arranging these similar parts to each other. Also, just in terms of the naming conventions, just like it mattered the order in which we did it when we had congruent triangles or congruent polygons, this would suggest that RS relates to the XY, which notice is in fact what we saw in my proportion as well as in our diagram, like so. And then even like if I look at first and last, RT and XZ, those are also the sides that correspond. So the name has to have corresponding parts lining up with one another. Let's see. Turns out corresponding lengths in similar polygons, that if two polygons are similar, then the ratio of any two corresponding lengths in the polygons is equal to the scale factor. All right, equal to the scale factor. And as a result, we can then now start solving problems. So let's take a look at example 2. This is what we got. So in the diagram, triangle DEF is similar, right? Get used to that symbol there. Probably going to write congruent for a couple days. To triangle MNP, find the value of X. Now, because these are similar, I don't know anything about what these individual angles are, but I do know that this angle is congruent to that angle. I know that this one's congruent to that. They're not going to help me solve this problem, but I figure we might as well remind ourselves that that's true. And regarding these side lengths, this is my little cheat notation. If I want to find X, what side does that correspond to? Yeah, the NP, the 30. So I'm going to say, remember when we used to label congruent, we would do it with a tick mark? This is my cheat notation. I'm going to label it with a tilde mark, I guess, little similar thing. So those two sides are proportional, and I can then compare them to either of the other two sides. So let's say I want to compare it to the 15. So here's double tilde, double tilde. So I'm going to say X is to 30 as 15 is to 18. All right, so once I know what relates, I can then set up the proportion. Wait, which one is smaller? What? Oh, everything is 1/5 smaller. So this is 4/5 of the larger one, or this is 5/4 of the smaller one, right? Sure. So you're doing it by scale factor, which is another way we could do it. Let's see. Yeah, you're doing it. Let's see. I'm going to reduce this before I do any work here. 15 and 18 are both divisible by 3. 3 goes into 15 5 times and into 18 6 times. So 5/6, right? Wait a minute. Yeah. So if X over 30 is equal to 5/6, what could I do to solve for X? I could do the cross multiply trick, or since X is in a numerator here, I'm actually just going to multiply both sides by 30. Yeah, it's a teacher's cell phone reminder. Yep. You're like, you guys hearing this sick guitar riff, or is it just me? 30 divided by 6 is 5. 5 times 5 is 25. You might have been off a little bit with your original estimate, but you had the right track. You had the right idea. So this is one way we could have done this problem. Another way could have been using scale factor, like you said. I could have found the scale factor K. Is it though? I think K would have been the 18/15. I think it's 6/5. Or oh, that's why you're 1/5. Okay, so it's 1/5 more. Well, let's find out. If K is 6/5, another way I could have found X, I went from this direction for my K. Okay, I did final over original. So I could have said that Kx is equal to 30. Or, right, I could have, if I replace K, that's 6/5 x is equal to 30. And to solve for x, what's another way I could deal with multiplication? Yeah, there's multiple ways you could do this. Instead of multiplying by 6/5, the inverse would be divide both sides by 6/5, but that's weird. So you could also have multiplied by its reciprocal. And I'll end up getting the same thing. So I'd get x equals 30 divided by 6 is 5. 5 times 5 is 25. All right, but because I knew they were similar, I'm then able to, right, make all sorts of wonderful conclusions as a result. All right, so you guys, like, we saw a little bit of similarity showing up back in our days of dilations. All right, in the diagram, these triangles, TPR, so those are the larger of the triangles, the non-right triangles. Oh, are these isosceles triangles? Someone across the hall. That is. We can shut our door, actually, if you want. So triangle TPR is similar to XPZ. He's actually going to investigate. So it says find the length of the altitude of PS. So guys, check this out. If these triangles are similar, linearly, there is a scale factor relationship between them. Okay? I could deal with their entire sides, right? I could say that, okay, if they're similar, then 12 is going to compare to 16. But I can also deal with any of their individual linear components. The ratio of 16 to 12, all right, for my scale factor, 16 to 12, is actually going to be the same as the ratio of 8 to 6. Right? Do you guys agree? Does that make sense? And that's going to reduce to 4/3. My scale factor is 4/3 to go from little triangle to big triangle. And any other linear dimensions that I want to compare between these will also have the same scale factor. So if I want to call this length the altitude x, to get from x to 20, I actually could use that scale factor. Or I could have even set up a proportion. So I either could have used 4/3 times x is equal to 20. That's one way. Or I could have actually set up a proportion from the beginning. I suspect that this right triangle is going to be similar to this right triangle. And I could have said x is to 6 as 20 is to 8. That's another way I could have set it up. Right? Long leg to short leg should equal long leg to short leg. And actually, there's all sorts of ways you could set this up to solve it. I also could have said, yep, that also would have been 4/3. Yep. Oh, you're solving it already? I don't know. Maybe? Probably. Another way I could set this up, I like to usually work within a single triangle, saying x is to 6 as this is to that. But I actually can also work across triangles. I could have said x is to 20, right? Long leg is to long leg as, what do you suspect would be in this next fraction? As 6 is to 8. Short leg is to short leg. So there's actually a whole bunch of different ways that you can solve these. The key is that when you set up a proportion anyway, you compare similar things to similar things. So in my numerators here, these were both small triangle and the denominators were both large triangle. And then in any column, these were long leg and these were short leg. All right, and as long as I compare similar things to similar things, it'll all work out. Let's actually solve this because that's what y'all came for, isn't it? Isn't it? Let's see. I'll reduce these. 4 goes into that 5 times and into that twice. Did I do that right? So x over 6 equals 5/2. Yep. And then multiply both sides by 6. You could cross multiply. If you want to just cross multiply every time, you can. Sometimes it's a little more work, but it's always reliable. 6 divided by 3 is 2. 6 divided by 2 is 3. 3 times 5 is 15. Scale factors. Good stuff. All right. Well, I'm showing you multiple approaches, right? So then you can think about all of them. Turns out, so I just made the claim that if two figures are similar, not only is there a scale factor between all of their sides, but I said any linear dimension in them will have a scale factor from one to the other, including perimeter. All right, perimeter is just the sum of all of the sides. If there's a scale factor to go from one to the next for each individual side length, then adding those all together, the perimeters should actually have the similar scale factor as well. Okay, so if two polygons are similar, the ratio of their perimeters is equal to the ratio of their corresponding sides. So the perimeter of one would be the sum of all of its parts, right? And that's going to be the same as the ratio of any of their sides, which is also equal to just k, the scale factor. Right? Do you believe it? Do you believe it? Okay, example 4. It's amazing. Example 4. Sorry. All right. I'm feeling it. We're in a new chapter. Okay. A town plans to build a new swimming pool. Hooray! An Olympic pool is rectangular with a width of 50 meters, a length, I can't read, a length of 50 meters and a height of 25. The new pool will be similar in shape to an Olympic pool. Kind of like how my body is very similar to Michael Phelps's body. Man, no. Like, I'm assuming he's more muscular and bigger, but actually there's no similarity between us either. Like, the proportions are probably all different. Really? Fins are good swimmers, you're suspecting? Sharks have fins. Up. All right. All right. Yes. All right. Into the shape, similar to the shape of the Olympic pool, but will have a length of 40 meters. So, okay, so this is the Olympic one. Olymp. So our new pool is going to be similar, except it will be 40. It says, find the perimeters of the new pools. Okay, well, let's find the perimeter of the first pool. Perimeter formula, by the way, for a rectangle, you could do length plus width plus width, or you can just do 2L plus 2 dubs. I don't know if you knew that one. Because, yeah, the width shows up twice, friends. So for the perimeter of the Olympic pool, we'll call that PO. That's going to be 2 times 50 plus 2 times 25. So that's hundo plus 50. So that's 150. So P naught. P sub 0 is 150. So check this out. Let's see if we can set up a proportion. The perimeter of the new pool, or town pool, PT, over 150, the perimeter of the Olympic pool, that should equal what? We haven't even jumped into area yet. That's the perimeter ratio is actually going to be the same as the ratio of any of their linear dimensions. So I'm going to say the town's length over the Olympic length. Right? So if I'm going to solve for the town perimeter, I can just cancel out those zeros there. Multiply both sides by 150. Both of those are divisible by 10. That's just a nice divide by 10 trick. It's a good trick, isn't it? Yeah. So the perimeter of the town pool is going to be 150 divided by 5. Let's see, divided by 10 would have been 15. Divided by 5 is twice as much, so that's 30. 30 times 4 is 120. And that's measured in meters. Nice. Meh. Now, you mentioned areas, and I actually talked about this before. I flash forwarded this idea at one point, but it turns out that the ratio of the areas is not equal to the scale factor. It's equal to the square of the scale factor. Yeah. And I think I've mentioned that to you before. But the area of a figure is not a linear dimension, right? Area is measured in some sort of units squared. And so if all of the linear dimensions were scaled by a factor of k, the areas are scaled by a factor of k squared. Okay? And I think we talked about that even with like mid-segments, right? We talked about like inside of a triangle, if you draw all the mid-segments, you get 4 smaller triangles, and all of their side lengths were half as much, but the areas were a quarter as much. You guys remember that? Yeah, you remember it. I'm flashing back. All right, last example for today. And it's not that hard. And actually, you guys might even be able to expand this to 3-dimensional thinking if you want. I'll let you think about that for a minute. Okay, in the diagram, these 2 triangles are similar. Find the area of triangle def. So area of def. I disagree. So the scale factor is 5/10 or 1/2. Okay? If I want to find the new area, it's not going to be half of that. It's going to be 1/2 squared of that. 1/4 of it. Yeah, it's true. It's true. So you could have said, so a def multiplied by k squared should equal 36, is one way you could do that. You also could have set it up as a proportion. We could have said the area of triangle def over 36 would have been the ratio of 5 to 10, all squared. Okay? I don't know. I think about it every time about hole punching tests. So let's see. So area, I'll just call that now. So I think your education is worth it, though. So multiply both sides by 36, and yeah, you guys got the 9. And 9 is measured in what? Yeah, centimeters squared. Well done. All right, thanks for watching, mis amigos de internet.